So in this video, I want to do the review of chapter 14 for the test coming up. And the first problem we see for chapter 14 is here at number 7 on page 2 of the test review. And it's kind of classic organic chemistry, a couple of nomenclature styles here, where in one, right, you're given the name, you want to draw the structure. The other one, obviously, you're given the structure and you want to name it. Now, the functional groups in chapter 14 include carboxylic acids and esters in terms of nomenclature. There's also the amines and the amides, and those are just being able to recognize those functional groups. And we'll see some of those examples here in a few minutes. Now, one of the amine structures that we did talk about in the context of nomenclature is aniline. It's that aromatic amine. So it has an aromatic ring, and it has a NH2. Right? There's an amine functional group, right? And then for the meta-methyl portion, well, I could actually name this differently. So when you're talking about aromatic compounds, and specifically I'm referring to the di-substituted patterns, you could use numerical values to show where the relative positions are for the groups. So in this case, 1, 2, 3, and the methyl group would be at that position. But you can also use the meta, ortho, or para to indicate the di-substitution pattern. If the methyl group had been at the number 2 position, that would be ortho-methyl aniline. If this methyl group had instead been at the number 4 position, it would be para-methyl aniline. Now this compound up here, we can see it's a carboxylic acid, right? So the oic acid ending indicates that. Buta, so there's 4 carbons. Let's just go ahead and get that out of the way. So there's our 4 carbons. I'm going to just put the carboxylic acid group on this end. I could put it here just as easily. And then at the third position down, third carbon down, we have 2 methyl groups. So 1, 2, 3, and there's our 2 methyl groups. And I want to go back in and then add the proper number of hydrogens here. Notice this carbon already had 1, 2, 3, 4 bonds to it, so there's no hydrogens attached to that carbon. Now, there's actually 2 other ways that I can think of drawing the structure. Notice on this carbon here, right, we have 1, 2, 3 methyl groups. So it's not, unusual to do something like this. Or I'll also use a condensed structural formula for the carboxylic acid. So when you come across this kind of, the use of the parentheses, you have to interpret, well, where are these items attached? Well, they're attached to the, next closest carbon. 3. Again, 1, 2, 3. So you have to realize that one of those methyl groups is actually part of the longest carbon chain there. Now, the other way I could draw this is in the bond line or the skeletal formula. So I've got 4 carbons, 1, 2, 3, 4. There's my carboxylic acid group. Still 1, 2, 3, 4. Third position, I got 2 methyl groups, and that would be it. Hexyl formate. Okay, so what we have to realize here, this is an ester. Formate has this structure. So if I was just to say, let's say the formate ion, well, that's taking, formic acid and deprotonating it. So it has this kind of look to it. Now remember, in the nomenclature for this chapter, the 8, there's 2 different forms that we see with 8, the ester form and the carboxylate group. So we borrow the nomenclature here. What you have to realize here is that the formate here, just 1 carbon, instead of having a negative charge, it actually has this hexyl group attached to it. And then so 6 carbons. So notice, you might be tempted to call this an aldehyde. It's really not an aldehyde. When you introduce that oxygen on the other side, this is an ester functional group, okay? I would not call this an aldehyde. Another way to draw this would be, say, you could even do the oxygen and then a zigzag of 6 carbons. So 1, 2, 3, 4, 5, 6. Again, hexyl is this group. Another aromatic compound that we found in this chapter was the benzoic acid. So it's this portion here. And, well, there's that di-substituted aromatic ring again. So I could say 4-chloro, that would work. Or I could also, put para in the front there instead of the 4. While we're looking at carboxylic acids, let's just go ahead and take care of this one. It's a fairly simple one. Right? We use prop as our base name for 3 carbons. Right? And then we just have this oic acid ending to indicate the carboxylic acid. This last one here is an ester. And just like the situation here, look at the breakdown. So the first name is actually associated with if you look at like a esterification reaction, it's the R group associated with the alcohol. Okay, we'll see those reactions in a few minutes. And it's actually this portion here. I'll just keep it highlighted in red. The part that's associated with coming from the alcohol is the one with the single bond sitting there. So this is going to come first. So I'm going to call it propyl. And now we would say, like the name associated with the parent name, if you will. 2 carbons back in chapter 11 was like ethane. Here it's going to be ethanoic acid. I'm sorry, ethanoate, since it is an ester. Now, just like with formate being a common name for 1 carbon, like for example, I could also have called this methanoate. There's a common name for 2 carbons, it's acetate. So I could have also named this propyl acetate. Question number 9 is in reference to the last 2 problems. So which one's the most soluble acid? Well, let's just take a quick peek. There's not that many acids here. There's one up here that has 6 carbons. This one has 7 carbons. This has 3 carbons. So the smallest molecular formula, the molecular weight is going to be the most soluble. And what I want to do with it is to put the delta negative and delta positive on it and then show how it interacts with 3 water molecules. So let's do that. We'll try to squeeze it into the first part of this blank area. Now, to show this notation properly, I really need to open up the condensed structural formula around the functional group. So let's do that. Delta negative, right, that indicates a partial negative charge. And that's always associated with the atoms that are electronegative. And electronegative atoms here are the oxygen atoms. And what we say is that, right, the electronegative atoms distort the electron density, pull electron density toward themselves. So if it gains a little bit of extra electron density, creating a delta negative charge, then the atoms attached to it is going to have a delta positive charge. And it would go for the hydrogen there and the carbon. Now, for the purpose of this class, we really don't go any further than that. So we only focus on just the atoms connected directly or bonded directly to the electronegative atoms. And then for our water molecule, what we need to realize and remember is that water, H2O, has that structure. And the reason why I drew it like this is, well, because same kind of deal. Delta negative on the electronegative atom, delta positive on the other 2. And there we go. There's that interaction. Right. In our universe, for whatever reason, positive is attracted to negative. Doesn't matter if it's a full-blown positive and negative charge like in an ionic compound or a partial negative and partial positive charge like we would see in, and I didn't ask for it up here, but this is a hydrogen bond. If something's going to dissolve in water, hydrogen bonds have to form, pretty much. Okay. Now, the problem wants me to draw 3 water molecules. Let me just do that. I turned this one around a little bit because the delta negative is going to interact with that delta positive there. And then here's the same thing, delta positive on hydrogen, delta negative on the oxygen. And then moving on to the second question here, we want to take the same acid, and here I am going to just condense it, react it with water. We can call that hydrolysis reaction. Remember, this is an acid-base reaction, so this is our acid, water's our base. Propanoic acid is not one of our strong acids, therefore it is a weak acid, so we're going to use our double-headed arrow, and we have the proton transferring in this manner. Okay, so it takes hydrogen and a proton, takes this off. And then what's left is that we have a negative charge on this one. This would be the carboxylate ion. And then once the proton bonds to that water, then it is the hydronium ion. And I'll go back and name those in just a second. But to finish off this set of labels here, the acid, once it loses a proton, we refer to that as a conjugate base. And then the base, once it acquires or accepts the proton, then this is our conjugate acid. And again, this isn't asked for in the problem, but this would be called propanoate ion, and then this is hydronium. Right, well, this is chapter 10, basically. If you have an acid, it goes in a solution, you are going to get hydronium ion forming there. The next question is dealing with some chemical reactivity from chapter 14. So this is our carboxylic acid. This is our alcohol. And what it does is it forms an ester plus water. So this is one of those condensation reactions. This would be known as esterification. It is an equilibrium reaction, does require a little bit of acid to get the reaction to take place. Right, and remember what happens here. It's the R group on the alcohol that basically replaces the hydrogen on the carboxylic acid. Something I mentioned, I think in the Lab 25 video, this class is not dedicated to analyzing the deep, structural changes that are occurring in the mechanism for these reactions. That's not what we do. If you ever take the 2-semester organic course, what you'll find out is it's a much more complicated story here in terms of the reactivity between the two reagents here. Again, we're just trying to identify where does that R group go? And then what forms? Well, what forms, so we have this hydrogen to account for, we have the OH to account for. What is it looking like? Well, you guessed it, right? It looks like the water. That's why we're calling this a condensation reaction. And then, by the way, the reverse process is referred to as a acid hydrolysis. Now, the second reaction here, this is a base hydrolysis, also known as saponification. So it's a hydrolysis. We're still breaking apart. Lysis, it's like to break in Greek or Latin. I think Greek. Doesn't really matter. What's going to happen? You can imagine the molecule getting cut right there. Again, this is not designed to show you all the details of the mechanism, just how to work through the problem. When this all rearranges, what's going to happen is that you're going to wind up with an oxygen with a negative charge associated with the carbonyl group. So it's a carboxylate salt that's going to form here. Plus, you're going to reform the alcohol. And to be consistent, I think, with the rest there. Now, there's one little tidbit that's not accounted for. It's that sodium. And oftentimes you see this. And then you also see the charges circled a lot of times. Kind of help distinguish between the plus on a chemical reaction and the plus on a charge. Let me just go ahead and name this while I'm looking at it. Sodium acetate. Right, it's a salt. Salt nomenclature, the metal cation comes first in the name, and then the anine's name comes second. I could have also called this sodium ethanoate. Last thing I'll say, this is not a reversible reaction. It's a one-way street. You have to change the chemical environment here before you could reverse back to get the ester to reform. Now, this is just a little practice in terms of identifying amines and amides. So let's just do the amides first. It really doesn't matter too much. One reason why I like the amides is because it has a very distinct feature. It has that carbonyl group attached to it. These other things that are attached don't really matter. Like, for example, I'm just looking for this pattern. I see the pattern there. I see the pattern there. Nitrogen, yes. No carbonyl group. Nitrogen, yes. Carbonyl group. Now, I'll just say this. There are other functional group names for this. All right. But we're just looking for this particular pattern. And if we see it, we're going to call it amide. Like here. There's another amide. All these other nitrogens, well, there's no carbonyl group attached directly to it. Therefore, it's going to be an amine. So the amine has 3 bonds to it, and at least one's just a regular carbon. Again, no carbonyl. And then for those amines, what you have to do is you have to decide the classification for each one. That's really just saying how many carbons are attached directly to that nitrogen. So let's do that for this one here. So there's the one carbon we see. Bond line structures, well, we know that each bend in the line here is going to be a carbon. So this is actually a tertiary amine. On this side of things, and actually these two are really the same because they both have, like this nitrogen has 2 carbons, this nitrogen has 2 carbons. And we're going to say both of these are secondary amines. And the same thing here. Carbon, carbon, 2 carbons, 2 secondary amine. There are some other common functional group names associated with double bonds with the nitrogens there, but we're not worried about those. Again, we're just after 2 different patterns to distinguish these 2 categories. That's it. The rest of the questions here are dealing with chapter 15, and we'll see that in the 3rd video coming up. Okay, thanks. Bye.